Okay, I think now we should begin our class today. And today we invited the scientist from Canada, the University of British Columbia. Uh, Her name is Shuhui Wang. So, uh, Shuhui Wang, could you share your screen to
Yeah,
us?
of course. Yeah. I can share my screen right now and
And all of the students come so you can begin your class. Thank you.
oh, okay. Um, so can you all see my screen now?
Yes, everyone, if you have any question or some advices or other, you want to
Yes, we
say,
can see this
you
screen.
can, yes, type your question or other advices to in our box, WeChat box.
Okay. Okay. Yeah, and so we can start right now. Good morning, everyone. My name is Shu Hui, and thanks for the invitation from Professor Wang, and I'm more than pleasure to give this short introduction about the research that I currently focus on, which talks about the wildfire trends, the burn severity, and associated hydrological responses. And in today's topic, I will talk in the following three part. And part one is talking about the trends of the wildfire activities, which including the Canada fire activities and the British Columbia fire activities, which I currently working on. And then secondly, I will talk about the record-breaking 2023 fire. And in the part two, I will talk about the burn severity. And I will talk about what is burn severity and the drivers of burn severity behind and how to access the burn severity. And the part three, I will talk about the hydrological responses to wildfire, like the mechanism and processes behind and the hydrological responses afterwards. And lastly, I will talk about the climate and fire interactions. And we'll come to the part one, and I will give some examples of the burn severity assessment from the McDowell Creek watershed in my neighborhood. It happened the wildfire in 2023. And, when I booked the flight from China to Canada, my flight almost get canceled because of this fire. And I was kind of, the wildfire is affecting our school, and some of our students have, faced some evacuations at that point. So the first one I will talk about is the area burned in Canada. So the graph above shows the area burned in Canada between the 1983 to 2023. So from the figure, we can see from the graph that the fires in 2023 set a record, burning more than 80 million hectares of land. However, if we exclude this year from the graph, we cannot give a specific conclusion about the trend in the area burned during the 1983 to 2023. That is because there are often century-long fire return intervals in many ecozones in Canada and large annual variabilities in burn areas. So the short-term trends, like the trends during the 1983 to 2022, as shown in the figure, need to be interrupted with the Caucasian. However, some researchers have found that area burned in Canadian forests are projected to increase more than 70% by the end of this century. So it's kind of crazy, right? And the second part, I will talk about the increasing burn severity potential in Canada. A research that recently published in Science has found that there is an increase in burn severity potential in Canada. So from the figure, we can find that there are significant increase in the number of the high burn severity days was found in the most recent 20 years, which is 2001 to 2020, compared with the preceding 20 years, which is the 1981 to 2000. So during the 2001 to 2020, the Boreal Cordillera, which is this area, had the largest proportion areas with the significant increases in the high burn severity days. So I will give you an example, like we consider this red area. The number of the high intensity fires has increased by 2 to 4 days in the past 20 years compared to the period 1981 to 2000. And as I told that the Boreal Cordillera has the largest potential of the high burn severity, it can be shown in this figure, in the figure on the right. And secondly, I will talk about the increasing area burned in British Columbia during the 1905 to 2020. And this was research that published on the Communications, Earth and Environment, which is a journal from the Nature portfolio. So the figure on the right first shows the date 2% burned, and this is the area burned over a period between the 1920 to 2020, while the figures on the left shows the trends in climate indices, which including the spring temperature, summer temperature, spring precipitation, and as well as the summer precipitation, and lastly the spring climate moisture deficit and the summer climate deficit. And I need to forget to introduce the date 20% burned, which is the date at which 2% of the cumulative annual area burned is reached. Like for a specific area, a fire needs how many days to reach its 20% of this whole area burned. And we can see that this figure shows a decreasing trend, and it's indicated that for the specific area, a fire needs less days to burn 20% of this area compared to what it used to be. And this figure shows that after a century-long decline, fire activities increased from the 2005 onwards, which coinciding with a sharp reversal in the wetting trend of the 20th century, like the spring temperature and the summer temperature has increased. I think it's 1980s, yeah, and the spring climate moisture deficit and the summer climate moisture deficit has also reversed afterwards. But you can may have some questions about the spring precipitation and summer precipitation. Like, although they have increased after this long period, the spring climate moisture deficit and the summer climate moisture deficit has increased due to the rapid warming and increased evaporative demands, and this cumulatively results in the area has burned. Like the fire would be more intense in the future, and we will burn more areas. And lastly, I will talk about the unprecedented 2023 wildfire season and the potential drivers behind. And so as the result is based on the research published on Nature Communications in 2024, the researchers have found that the 2023 wildfire season in Canada was record-breaking in its scale and intensity, spanning from the mid-April to the late October and across much of the forest regions of Canada. And they have attributed this record-breaking fire to several environmental factors that coverage early in the season, like the early snowmelt, the multi-annual drought conditions in the West Canada, and the rapid transition to the drought in the Eastern Canada, while the anthropogenic climate change enabled the sustained extreme fire weather conditions. They find that the May to October mean temperature over Canada in 2023 was 2.2 Celsius degree higher than the 1991 to 2022 average. Okay, so I will give a short introduction about the McDougall Creek wildfire that happened in 2023, which happened on the evening of the August 15, 2023, and this fire was discovered approximately 10 kilometers northwest of the West Kelowna, like this area. And the fire quickly escalated due to the strong winds and extreme drought conditions, becoming one of the most destructive wildfires of the 2023 season in British Columbia. So by August 17, the powerful wind gust caused the wildfire to spread rapidly across the mountains, and it's reached to the Kelowna area. So the fire jumped the Okanagan Lake and sparking new wildfires north of the Kelowna and triggering a state of emergency. The evacuations were ordered, and Kelowna International Airport, as I said before, has suspended flights due to the worsening conditions. And as of the September 1, the wildfire has burned like the 13,000 hectares and remained out of control. It was not until September 21 that the BC Wildfire Services report that wildfire was being held, meaning it was no longer expected to spread under current conditions. And despite this, several regional parks remained closed until October 3. And the McDougal Creek watershed has its over 60% area burned, and in this fire event, and it provides a notable opportunity to explore the burn severity due to the roadside accessibility. We can find there are some roads that has across the burn scars as shown in the figure on the right. And in the August 2024, our research team made a short field observations in this area. And here is the part 2. We will talk about the burn severity. And I will also using the example from the McDougal Creek watershed. And firstly, I will talk about, as I said before, what is burn severity and what factors influences the burn severity. And in this part, I will give you some, some papers that published in some well-known journals like the Science and Nature Communications, and talking about the factors influencing the burn severity and giving their importance a ranking. And lastly, I will talk about how is burn severity measured and accessed. So what is burn severity? The burn severity is the effect of the fire on the environment, and it's a way to measure the changes in vegetation and the soils after the fire. The burn severity is kind of but different to the fire intensity, which describe the amount of energy released from the fire. And it's kind of difficult to measure the burn intensity. The flame length is often used as a proxy to access the intensity. And so the burn severity is largely driven by the degree that the fire burns into the ground, and the low severity fire doesn't burn deep into the ground, and the vegetation will recolonize more quickly, while high burn severity, as shown in the figure on right, burns deep into the ground and may expose the underlying mineral soil, making it easier for dioecious trees to recolonize the area. So the burn severity is driven by a large of factors, like I said before. So because of this, the burn severity is patchy within the fire parameter, which is a mix of size ranging from the unburned to high burn severity. So from this figure, we can find that in this red area, we can find that there are mineral soils has exposed after the fire, while for this area, we can still find some vegetations. And in this area, we can find that there are just brown pixels we can consider. So based on these satellite images, we can, roughly access the burn severity according to this. Like this area, we can see that they experienced the low burn severity, while this area, we can consider that they have experienced a high burn severity, a high severity burn, sorry. And so the degree of the burn severity can have the long-lasting implications for what type of the vegetation regenerate after fire, and therefore the wildfire species that will use as an area post-fire. So, and on top of that, the burn severity is best accessed the summer following a fire. So if the severity is accessed too early, the damage caused by a fire, such as the plant mortality, will not be observable. And if it is accessed too late, the fire's impact will not be visible due to the vegetation regrowth. And and I will talk about the key drivers of the fire behavior and the burn severity according to the papers that published. So they can roughly classify into 3 categories. And the first one is the vegetation, which they will use the fields in their paper. And secondly is the topography, like the slope, elevation, aspect, etc., etc. And last is the weather. And meanwhile, the burn severity also affects the landscape and can alter the vegetation type, the soil properties, and the recreational and subsistence opportunities. And the key drivers, the first one is the vegetation. Like the vegetation provides the fuel, which including the duff, as shown in the figure on the right, and the fine fields and the woody fields. And I will give some descriptions about these 3 terminology. The duff is a subsurface layer of slowly decomposing moss lichen and litter. And in the boreal forests, the depth is often about a foot depth and is a primary driver of the burn severity. The deep turning of depth that expose the underlying mineral soil is a key indicator of the high burn severity. And the fine fuels, such as the grass and the twigs, can lead to the fast spreading fires. The fires involve mostly fine fuels tend to be low severity, and the woody fuels are thicker and burn longer and release more heat than the fine fuels. So when the fire is hot enough to reach the entire trees as well as the surface fuels, it is also called crowning or torching. And at this point, the fire intensity and its potential to grow rapidly and spread embers across a long distance is dramatically increased. And the fire can become a crown fire, where fire spread from the treetop to the treetop. So the dove is a unique fuel bed where wildfires can burn deep below the surface and smolder for days or weeks in the boreal forest, and reigniting fuels at the surface when the weather conditions become favorable. So this make it impossible to have high burn severity where the dove is burned to mineral soil, but flames do not get into the trees. And this can happen when the fire smolders in the dove over time, consuming it without producing the tall flames. And the trees can fall, sometimes even with intact green needles and leaves, because the fire burns the roots and the top layers of the soil supporting the trees. The fires can smolder in the dove back below ground and it can reemerge, as I talked before. Sometimes it can, smolder for the entire winter. And while the fire's consumption of the soil layer is a primary component of the burn severity, as the dove is an indicator, the fire's effect on the trees themselves is also a factor. Sometimes trees to be killed even by the low-intensity fire, but how high the fire burns into the tree canopy is considered when assessing the burn severity. Like this figure gives a canopy fire. As I talked before, it often happened in the high burn severity fire, while in other times the trees are not killed by the direct contact with the flames, but rather due to the heat generated by the fire. And this results in the trees with the brown dead needles still attached, as shown in the figure on the right. And this figure was taken in the McDougall Creek watershed when we were doing the field survey. So from the figure, we can find that this tree was not torched, but it's still dead with the brown dead needles attached. So we can assume that these trees may be killed by the low severity burn, sorry. And on top of that, the needles and branches of the conifer species are flammable in part due to the presence of the aromatic resin that permeates the whole tree and allow fire to quickly spread to the top of the tree. The figure here gives an example of the aromatic resin from the Douglas fir. So if the trees has the fires are more flammable if they meet the trees that have the aromatic resin. And secondly, I will talk about the key drivers, another key drivers of the burn severity, which is the topography. So studying the burned areas helps researchers determine which topography features contribute to the burn severity. Therefore, they have, some effective measurement strategies that can to buffer the high burn severity fires in the future. And this figures gives like the topographic characteristics in the McDougall Creek, and the first one is the elevation, and the second one is the aspect. The third one is the slope. So according to the research, they all have an impact on the burn severity as shown in the figure on the right. So the aspect is the direction that the land faces. The south-facing slopes are warmer and get more sunlight, while the north-facing slopes are cooler and receive less sunlight. In the third slope, directions allow for the growth of the vegetation that can favor or suppress the fire. And the slope is the steepness of the land. The stepper slopes can cause fires to move quickly upslope as a result of the hot air rising and the drying fuel sources up to the hill from the fire. And conversely, the fire moved down steeper slopes more slowly than more gradual slope. So the terrain, which is the natural scenario, can create natural barriers that can act as a natural fire break. Examples of the natural fire breaks includes the lowlands areas along bodies of the water that can have a high amount of the moisture, or like some rocky areas that do not contain fuels to allow fire to spread. And the elevation is the height above the sea level and can affect how fire behaves. Like the areas of the low elevation are generally warmer but contain more moisture, while the areas of higher elevation tend to be cooler but drier. So, according to these topographic characteristics, the fire suppression efforts can be used according to the topography of a specific watershed. On top of that, the fire suppression efforts affect the level of the burn severity. This can make it more difficult to attribute the burn severity to landscape properties in sites that have the active fire suppression. And lastly, I will talk about the weather, which is also another factor that affecting the burn severity. The weather is a key driver of the fire severity, although the effects can be difficult to quantify. So for example, like the high, dry, and windy weather creates the conditions where fire can spread rapidly and burn intensely and be difficult or impossible to suppress. But as weather becomes hotter and fuels become drier, there is an increase in fire danger and greater effects of fire on the landscape. And in some cases, the researchers in Canada used the parameter in the Canadian Forest Fire Weather Index system to represent fire weather instead of using solemnly like the temperature or precipitation. And do you still remember the climate moisture deficit as we talked before? So from the figure, we can find that they use mainly 5 indices. Like the first one is a fine film moisture code, and it is calculated based on the temperature, the relative humidity, the wind, and rain. And the initial spread index is calculated based on the wind, and the depth moisture is calculated based on the temperature, relative humidity, and rain. And the drought code is like based on the temperature and rain. So this is a well-developed system consists of these 6 components that account for the effects of the fuel moisture and weather conditions on the fire behavior. And I remember in a recent paper that published on Science, and she used these 6 indices as the weather indices, which can, instead of using the traditional weather indices like the temperature and the precipitation. But I think the result is, the model that she trained in that paper is have a good performance. So, and we also find that the drought was the key drivers of the burn severity. So I think in different countries they have different fire weather index system, and I think when we do the research, we need to looking specifically into the local characteristics instead of using like the standard indices like the temperature or the precipitation. But I think in some areas that may facing the data shortage problems, like using the indices, in general indices like the temperature or precipitation, is also alternative solutions. And here I will give you 2 examples that talking about quantifying the key drivers of the burn severity. And the first, this paper was published in 2022 in the Geological Research Letter, and the study was conducted in the Rocky Mountain area. So they have investigated the satellite drive the burn severity from the 1985 to 2015 at the 30-meter resolution in the 3 mountain national parks in Canada, which including the Banff, the Kootenay, and the Yoho National Parks in the Rocky Mountain area. And the results shows that the fuel type as shown in the figure here, had the most significant influence on the burn therapy. Hitting the complex mechanism of the environmental controls on the fire behavior in this heterogeneous mountain region. And I'm going to show you the parameter they have selected. Yeah, and you can find that this is the variables descriptions of the predictors used in the models. The first one is the field type, like they talk about the vegetation type, like the spruce and lichen woodland, and the fire causes. I think is prescribed fire and the lighting caused fire, which is the natural caused fire. And they also consider the watershed characteristics, like if they have intensive management or intermediate management, which I think it can also considered as an urbanization level. And while talking to the topography parameters, they consider the elevation and and the topographic position index at the scale of the 300 meters. While talking about the vegetation, it talks about the crown closure, the living biomass, the conifer proportion, the dioecious proportion. While for the climate, I think they have used the spring degree days below the 18 Celsius degree. Yeah, and the spring mean maximum temperature, the winter relative humidity, and summer precipitation. But here we go. Yeah. So instead of using like these four indicators, the seasonal climate variables were also considered in her models, like the average winter temperature, the average seasonal, like the winter, spring, summer, autumn mean temperature. And I think it's the maximum and minimum temperature. Yeah, it's they do have selected a lot of parameters in their research instead of using this Canadian Forest Fire Weather Index in this paper. And I remember that I remember they used the model like random forest. The random forest model achieved a good performance in estimating the observed burn severity of the parks with a MOE of the 0.006 or 09. 0.06, and RMSE of the 0.12 and R square of the 0.67. And to be honest, I think this model's performance is not that satisfying because based on the statistic, I think the number is kind of too low. Yeah. Well, in their next research, they have expanded their study areas to the whole Canada. And so in this research, they have used this system as the weather index and the topography using the elevation, slope aspect, and topography position index. I think this parameter they also used in their previous journal, in their previous paper. And they have built a multi-nominal logistic regression model to estimate the remotely sensed burn severity for the 10 Canadian ecozones. Sorry, I forgot to introduce this part. And this also talks about the parameters used in their model, which talks about the few vegetation type, which including the biomass, cone closure, height, and conifer spaces covers. So we go back to the model part. And they built the multi-nominal logistic regression models to estimate the remotely sensed burn severity for the 10 Canadian ecozones, as shown in the figure on the right. And the multi-nominal logistic regression is, I think it's a part of the machine learning models, but I think it's like a more traditional statistical model, and it can consider as the part of the general general logistic regression model. So, and from the figure, we can find that, from the figure on the left, you can find that in most ecozones, the fuel, the fuel and the weather has the preceding effects on the burn severity. And the relative importance of the predictors in the models was like the weather and the fuel, but the topography is kind of different from their previous paper. We didn't find its importance, like the leading importance in these 10 ecozones. So the result is kind of different from their previous paper. And I think this gives us, like the inspiration. So when we were doing our research, that we need to take the research skill into the considerations, and the research skill does have effect on the conclusion, on the result. And here we will talk about the burn severity affecting the post-fire landscapes. And I will talk about regeneration and succession. Like the depth of the burn has the major influence on the subsequent regeneration, which is the short-term growth and the succession. And it's talking about the species composition of the vegetation. And here I will give you some figures that we observed in the McDougall Creek watershed that has the burn scars that has different burn severities. First, the figure on the left shows the area that has experienced a low burn severity burn. We can find that the fireweeds and other herbaceous plants often resprout from the below ground and roots in a low or moderate severity fire. And the figure here shows an area that has experienced a high burn severity burn. So in the high severity burn areas, the fire's regenerates tend to be from the seed dispersal. The new organic layer allows the shrub species and the young trees to grow in the area. As shown in the figure, we can find the new spruce in the photo. However, in this high severity area, the young trees will continue to grow until the area transitions into a forest with large trees that are able to outcompete the shrub species. And over time, the vegetation will continue to grow until enough fuel accumulates to support a fire and restart the regeneration process. And finally, I will talk about how to access burn severity. As I talked before, the burn severity is typically divided into like the low severity, moderate severity, and high severity classes. And I will show you some pictures during our field trip in the McDougall Creek watershed and the burn scars of different burn severities. The first one, this is the low burn severity photos. So from the plots, from the field survey plots notes, we can find that the trees has been scorched while the shrubs are mostly alive. The patches of dove have been burned. And we also find like some patchy surface fire, and we can find some regeneration species like the moss, the lupin. The lupin is the plant that can absorb the organic nitrogen from the air, and the fireweeds that we talked before, which sprout in the burned species, but not in severely burned area, and the wild strawberries. And we also find the rock shatters. But I think the professors told me that it may be not caused by the fire in 2023, and it can be caused by the previous fire. And lastly, we also find the moss are often binding with the soils and on the ground, so this can cause the repellency on the soil surface. And this is the medium burn severity area. So we have found that many trees have fallen and brown and dead, and some shrubs have survived, and the dove layer has burned evenly across, but not deeply. The herbaceous species like the wild fireweeds are already growing, and some vegetation species may grow in the area moving forward. So we also find that the mineral soils has been exposed by the fallen trees and the burned surface, which allowing the fireways to grow. And when we remove the dead needles and the twigs on the ground, and we find the soil underneath is water repellent. That is because maybe this area has developed a water repellency layer under the ground because of the fire. And lastly, this is the highest burn severity area. And from the figure, we can find that most of the shrubs have died and a large number of stuff has burned deeply. And on top of that, this area is a south-facing slope, which receives more sunlight, and therefore it can maybe increase the chance of the high severity. And the area around trees have been burned to mineral soils, like this area. And on top of that, we can find some soil erosion signs, like this, I think it's white. Yeah, it's white area. I think maybe caused by the soil erosion. On top of that, the ground has been so disturbed that after 1 year, only a few vegetation is growing in this area. And there are mainly 3 tools currently can be used to access the burn severity, and including the composite burn index, which is based on the field service, and the second one is a spectral indices, which talking about the changes in the ground cover during the pre and post fire detected by the satellite images, and the last one is the machine learning techniques, which often combined with the satellite image, and I will talk to you about it later. So the first one is the composite burn index. It measures the burn severity with on-the-ground field service. And, it's kind of time-consuming and regarded as the most accurate assessment. And the figure on the left shows a field survey for the composite burn index. So for this area, they often have select a specific area, and they will calculate how many vegetations are affected in this area. So the composite burn index classifies the burn severity by accessing the fire effects across the vegetation strata and creating a composite score. The fire can effects including the species mortality, the char height, the chances to soil and dust layers, and changes in the species composition. And the vegetation strata includes like the dominant trees, as shown in the figure on the right, and the intermediate trees, and the tall shrubs, the herbs, and the substrate, which is also dust. So the fire effects on each strata are scored on a continuous scale from 0 to 3 and averaged to create an overall composite burn index. The threshold for the values are later assigned so that the burn severity classes can be explained based on the ecological impact. And the spectral indices calculated burn severities using the satellite images on a continuous scale. And it's kind of like the composite burn index. The threshold value are assigned to differentiate the burn severity classes by the ecological effects. And one method is to look at the change in the ground correlation in the satellite imaging using a measure like called the normalized burn ratio. Like the greater the burn severity, the darker the ground will appear. So while in the about 2 figures, by looking at the changes in the landscape pre and post fire, a large amount of changes between the images, that means that this area was more severely burned. And the figure here gives an example of the West Kelowna, which is the area that had the McDougall Creek watershed located at. So from the satellite images in 2021, we can find that this area is generally not disturbed, and we have found many great pixels in this area. And after the wildfire in 2023 and the satellite images in the same year find that this area is turned into brown. So for this area, we can consider if they have more changes for the specific area, we can consider that they have experienced high severity burn. But a drawback of the spectral indices is the deep burning into the depth and the soil is not well detected because the satellite images often reflect the changes in the vegetation generally. And lastly, I will talk about a method, the machine learning method, which often combined with the satellite images to classify the burn severity better. So the machine learning classifiers can classify the burn severity using the entire spectrum and can utilize other factors. And this figure gives a framework for the integration of the random forest mapping approach into the fire management operations to routinely produce and improve the fire severity maps. And this approach outlines a flow work for like the production of the fire severity maps following the fire in this area. And I think it's also like the training data, like I think it's the composite burn index field plots and the aerial photography from the fires can be used to create a burn severity map shortly after the fire, allowing the land and fire managers to understand impacts of the fire had on the landscape. And the routine collection of the fire severity data for the initial map validation, which this part, which allows for the initial map validation and the necessary training. And secondly, talk about the continued assessment of the classifier accuracy to access the need for the correlation of additional training data. So this research is this figure is from a research that published in the Remote Sensing of the Environment in 2018. So from the current papers that I have read, I think the most frequently used machine learning techniques is the random forest in this research topic. And in this rapid changing environment, it is expected that fires will burn more land and more frequently, affecting more areas and starting earlier and lasting longer. And improvements in the burn severity assessment will aid understanding of the environmental impacts of the wildfire, which may benefit science-based decision making to better protect resources, lives, and property, and achieve ecological objectives. And here we come to part 3, and I will talk about the hydrological responses to wildfire. And here I will give a short synthesis of the global studies. And here the figure shows a visual summary of the wildfire effects on the forest ecosystem and hydrological processes at the watershed scale. So from the figure B, we can find that, I will give a short explanations about the terminologies. The ET here means the evapotranspiration. The SI means the soil infiltration rates, and the SH means the soil hydrophobicity rate. Q mean Q flat and Q low means the stream flow. And annual stream flow. And this is the peak flow and this is the low flow. So we know that the wildfires can cause large and long-lasting effects on a wide range of the ecological processes. The intermediate impact include the reduction in the canopy, like the understory and later layers, which lead to the reduced canopy interception, transpiration, and the evaporation. While the changes in the post-fire radioactive forcings can increase the soil evaporation. And this process generally results in an overall reduction in the total evapotranspiration. And the primary change in the soils following the wildfire is the reduction in the soil infiltration rates, which primarily caused by the ash deposition, the surface seal formation, and the development of the water repellency layer. As I think I give you an example in the previous, I think, in the figure that I've taken in the McDougall Creek. And Collectively, these short-term changes in the vegetation, soils, and associated water fluxes and functions often lead to the increased surface runoff and the changes in the groundwater recharge, which impacting the stream flow, magnitude, and timing. In the months and years following a fire, the vegetation and soil typically undergo a recovery process with the ET and the soil infiltration and the soil hydrophobicity rates gradually returning to the pre-fire levels. However, some studies suggest that the evapotranspiration may exceed the pre-fire conditions during the regeneration process, which can result in a decrease in the annual runoff relative to the pre-fire period. I think this research was conducted in the eucalyptus forest in Australia. That is because after a wildfire, the regeneration of the eucalyptus forest often demand more water compared to a mature eucalyptus forest, and this ultimately results in the higher higher demand on the water and decreased runoff afterwards. So I think this highlights the role of the long-term vegetation trajectory in regulating the post-fire stream flow processes. So of all the factors influencing the post-fire stream flow, the burn severity is often regarded as the key factor controlling the magnitude of the hydrologic responses. The post-fire precipitation dynamics is another influencing factors that usually explain much of the variability in the hydrological responses. And other influencing factors include the proportion of the catchment burned, like the post-fire measurement, like if this area has experienced a salvage logging and the revegetation, yeah. And here we talks about the total stream flow and the stream flow components, which are peak flow and the low flow responses to the wildfire. So, the wildfires are well known to increase the annual stream flow, with the magnitude of increase often positively correlated with the percentage of the area burned and the burn severity. And a global synthesis indicates that the annual stream flow increases range from 0 to nearly 2 orders of magnitudes after the burning. And this increase can persist for up to a median of 5 years. In contrast, some studies report no change or even a decrease in the post-fire annual stream flow, which particularly in the larger watershed with limited burn area or under anomalous post-fire climate conditions that mask the fire effect. And this part I will talk about later. So although the annual stream flow is generally expected to return to the pre-fire conditions after an intermediate post-fire increases, the persistent decrease are more common in the Australia, Asia, ash forest, as I talked before, because of the elevated evapotranspiration during the revegetation period. And the post-fire flood flows typically show increased magnitude and frequency, as well as early occurrence compared to the pre-fire conditions. Like, for example, a wide range of the flood flows increases have been observed in the United States forests following the wildfire in different regions, which shows that the strongly site-specific nature of the flood responses. And a recent analysis using the machine learning technique indicated the burn severity, the percent area burned, and aridity and soil type as the main factors contributing to the variations in the post-fire flood flow. And I think they suggest that changes in the post-fire flood flow are likely driven by the impact of fires on soil hydraulic properties, which particularly infiltration. And while talking about the low flow, some studies indicated that low flows increases in the short term after the burning. Some other researchers suggest that the post-fire conditions may reduce the groundwater recharge and consequently leading to the lower base flow and the low flow. And here we give you 2 examples from 2 papers. So this figure shows that after the fire, we can find that the low flow increases. And this paper was published in the Journal of the Hydrology in 2020. And other researchers find that the low flow decreases compared to the pre-fire conditions. And this research was published in 2020, and still in the Journal of Hydrology. And here I will give you an example of the burned forest impact water supplies across the corners, which is which is the whole area of the United States. Like, we have known that the headwater forests in the continental US are increasingly threatened by the longer wildfire seasons, which raising the concerns about water availability. And the hydrological responses remain unclear at this scale due to the differences in the fire characteristics, climate, the forest cover, and topography, etc., etc. And they just want to know, like, how do wildfires across the corners affect the fire flows given the varied watershed characteristics, the climate and the fire characteristics. The researchers evaluated wildland fire impacts on the river flow using a framework as shown in the figure. So, following a stepwise approach, they added progressively more data at each step to highlight various aspects of the post-fire river flow response and interactions with other parameters. At an initial assessment, the disturbance of the river flow and the water yield ratios, which is a Q to the P, was detected. P here is a precipitation. And next, the nonlinear relationships and the interactions between the burn air ratio, the watershed geometry, and the climate variability and the topography and land cover was found in order to determine their respect influences on the DQ. DQ here is the difference in the stream flow and the critical minimal variations of the burn air ratio, resulting in the river flow disturbance. And finally, the fire disturbance impact on the river flow from the climate variability impact was separated. And this was done by the means of attribution analysis of a subset of the burned watershed, for which a water yield ratio disturbance was detected. And this research was published in the Nature Communication in 2018. So we will talk about the result. And I think I forgot to talk about the background of this research. They talk about the changes of the annual river flow in the United States watershed burned at any time between the 1985 to 2006 or 2008, and the percentage observed change in 5 years mean annual flow, and the percentage. This figure here shows the percentage change attributed to the fire. Yeah. And the figure B shows the percentage change attributed to climate. And the figure C, I think, is talking about the percentage observed change in the 5-year mean annual flow. And the result shows that the annual flow in the 32 watershed with over 90% burn air ratio was affected by the wildland fires, which means that in this 32 watershed, they have over 19% of their whole watershed has been burned, and after the fire, the stream flow has changed significantly and detected by the framework they have developed in this paper. On top of that, they also find that the prescribed fires in the subtropical southeastern had no significant effects on the flow, which means that compared to the natural wildfires, the prescribed fires, which are often ignited by the humans, typically has no influences on the stream flow. And here we will talk about interactions between the climate and the wildfires and their interactions on the stream flow. the figure here gives an assessment of the wildfire impacts on the watershed, annual water yield. And this research was published in the Ecological in 2018. So I think the research was conducted in the 3 watersheds in different states of the United States. Like this is the South Cordillera, yeah, I forget the state name. Yeah, South Cordillera. And second one is Arizona. The last one is California. So the cyan bars, as shown in the figure, indicates the stream flow that responses to the post-fire climate variability. And we can find that the post-fire climate variability has different impacts on the different watersheds, like in the South Cordillera and the California states, the climate variability has reduced the stream flow. While the yellow bar here shows the wildfire's impacts on the post-fire stream flow. And in all these 3 states, we can find that the wildfires has increased the stream flow afterwards. And DQ means the blue one here shows the blue bars here shows the cumulative effects from the climate variability and the fire effects that effect on the post-fire stream flow. So we can find that in the South Cordillera states, Cordillera state and the California states, the climate effects have an offsetting impacts on the increasing effects from the wildfire. So ultimately, the stream flow during the post-fire period has decreased. While in the Arizona states, we can find that both climate variability and the wildfire has increased the post-fire stream flow, and they have cumulatively increased, amplifying the stream flow. And I think this gives us some inspirations, like when we are doing the research we need to really consider the watershed characteristics as well as the local characteristics instead of using a general result. Like the stream flow sometimes, the climate variability sometimes do have the offsetting and may mask the effects of the wildfire's impacts on the stream flow. And thank you so much, and thank you so much for attending this lecture. And if you have any questions, and please feel free to contact me. And I think we have the lecture takes around 1 hour, and I have also prepared a video for you, which talking about understanding variations in the wildfire burn severity to improve the fire resilience, which I think it talks about the pre-fire disturbances, like in some watershed in the British Columbia. They also affected by the mountain pie beetles infestations, and in these specific areas, they often exhibit different burn severity compared to the other, like, some health forest areas. And this video takes around 40 minutes to finish.
Hello, Shuhui. Maybe we can have a 10 minutes break, then we come back at 9:40. Have a break. Okay, 10 minutes.
Yeah, of course. And I will see you in 10 minutes.
Okay, you can. Yeah, someone maybe have a question for you.
Oh, yeah, of course. Yeah. Can you type here? Oh. Know that wildfire is occurring not because of the changing of the land uses and human activities traditionally in other areas based on the case wildfire in the peatland due to the changes land use and human activities from the rubber plantation to palm oil plantation. Urbanism from the water-sensitive settlement to modern urbanism, from the floating house and the water transportation to dry road infrastructure for car rubber trees could protect water. Palm oil trees absorb water a lot. Traditional communities and activities depend and protect the native landscape. And modern activities tend to contradict with the native landscape system. We change the landscape and we change climates. drastically. And my current basically try to see the culture and the nature as interconnected system real precision. Um, um, is the I think Vidya spacey. Okay, I saw your question. It's very not because the genius. Yeah, that's I think we can start now. And okay, I'll share my screen. Yeah, I can first share my screen now, and yeah, we can continue. As I told you before, I have prepared. I have found a video for you which talk about understanding variations in wildfire burn severity to improve the fire resilience. And this research was done by a professor in the University of the Northern British Columbia, and he dives more than into the watershed that solemnly experienced the wildfires, but also consider the previous disturbances like the mountain pine beetles infestations. And I think we can start now. Oh, you cannot hear the sound? Okay. Okay, I will help you. Still no. Why?
Then we're going to pursue further this question of why some stands, especially some juvenile, which I'll touch on briefly, and then our analysis of fire skips and fire refugia. So those are recorded if you want to go back and compare with what we found then and what we said we'd be doing with what we actually got done in the intervening 3 years. And we'll start off with some acknowledgements right at the top here. I'm really just a collator of information collected by other people who did all the heavy lifting, some of whom are in the room here today, and with funding by a variety of federal and provincial agencies and a lot of in-kind contributions. Okay, we're still in business. So I'm going to organize the talk around 3 main questions. First, talking about satellite-based burn severity. We have several indications that it should be refined. Then we're going to pursue further this question of why some stands, especially some juvenile pine plantations and some forest types, seem to escape crown fire in particular, and what those mechanisms might be as they relate to microclimate and fuel moisture. And then finally, how can we extrapolate from those results to talk about conservation planning, community safety, and forest management, for which we undertook some fire simulation modeling. So starting with satellite-based burn severity, you're probably mostly familiar with the use of these various indices, the difference or delta normalized burn ratio based on satellite images before and after fires, variously scaled or indexed to then provide themed color-coded maps, sometimes 3 classes, sometimes up to 7, as in this example here. And usually you'll see the green areas marked as unburned or low burn severity, scaling through yellow, orange, and red to the high severity burn areas. Now, those are done across North America. The BC government is now undertaking the mapping of all fires greater than 100 hectares. It used to be done sort of on a one-off basis. Now it's quite regularly done by forest analysis and inventory brand. And this has a lot of implications to further management, whether that be salvage, logging, or restoration. They should be calibrated, however, which we are not doing in BC. They should be ground truthed, essentially using some kind of ground-based burn assessment. And the standard currently developed in the States is the Composite Burn Index. That's a scorecard approach that has 4 components evaluating the degree of damage and recovery in the overstory, the understory, and in the substrates. Now, this is a truly ecological severity assessment because it looks at things like change and recovery in the understory vegetation. So it's not just a damage assessment. It's not really an impact assessment of the fire. Okay, it's often done year or years later from the fire. So we're talking about the ability of the system to rebound as well. So I'll talk about that a little bit later, but it generates scores. It's a lot of subjective weighting on a scale of 0 to 3. So here's some results that we found from our campaign of Composite Burn Index assessments. This work was led by Sam Coggins and helped out with by a lot of UNBC students, looking at some of our big fires in 2018 and the Plateau Complex from 2017. And we found that the difference normalized burn ratio did a very good job of identifying burned versus unburned forest. Okay, we could get that 87% correct. But categorizing these low, moderate, and high, you can see there's a lot of leveled off their CBI values. Not so good at determining. We can tweak those boundaries back and forth a little bit, and we could improve it for our
that's a question.
plantations.
All these
still playing with it for the broadleaf leading in different age classes of unmanaged forest. But the take-home message here is believe the burn versus unburned, not so much the higher burn severity metrics. Here's an example of some problems with the different forest types. On the left, we see a typical high severity burn area from the Nadina fire south of Houston here, the Nadina Lake fire. And you see charred stems, no twigs left, often a lot of bare ground because it was scorched right down to mineral soil. Contrast that with an aspen stand mapped as the same high burn severity. And you see tree crowns that do have their branches intact, no charring up the stumps, and a rapid recovery or regrowth of fireweed and blue joint reed grass coming in afterwards. So we're suggesting that the spectral signature that needs to designate high severity for aspen stands needs to be much higher than it does for conifer leading stands. So we played around with some of those and using some perhaps overly simpler linear regressions, came up with different thresholds for juvenile conifer plantations, mostly lodgepole pine, the broadleaf leading stands, and other natural conifer leading stands. And again, I would emphasize, believe the burned versus unburned mapping, and the overstory component of the CBI results, even though all of the literature, all of the work we've published and are trying to publish is emphasizing the full CBI score, because that's what's done. I'm suggesting that in many cases, we're more interested in just the overstory. Did the trees burn and survive or not? Not will the ecosystem come back? And that's important, obviously, for fire control, community safety, but also for timber management, because right now in BC, they've recently tried to streamline the process for salvage logging. And they're probably not and shouldn't go into the low severity burns because they're still mostly green. They're probably not, the industry doesn't want to go into the high severity burns because there's so much charcoal deep into the standing bowls. So they're going to be targeting the moderate severity stands. So we need to get this right in the long run. Okay, question 2. What about these plantations that seem to escape crown fire? And I thank Jim and Larry for pointing out this phenomenon to me some 5 years ago, which just didn't make sense because it seems to be contrary to all our understanding of high crown bulk density, canopy bulk density in continuous conifer stands as being more likely to burn. Yet these stands repeatedly show up as not being burned. Here's a picture from, again, the Nadina Lake fire. You can see those nice square cut blocks. Turns out most of them are about 20 to 40 years old. And here's another scene further west, also in that same fire. You can see that visual effect flying over, and it does show up in the burn severity theming that the province did as well. So a master's student and I, Andrew Boxwell, did a chi-square analysis of an overlay of the VRI and the burn severity maps, and concluded that, in fact, yes, for half of the 14 fires of 2017 and 2018 that we addressed, there was this significant difference. That is that H class 2 cut blocks survived, remained unburned more than you would expect by chance relative to the overall burn level within the fire perimeter. But it's a very small reduction in overall probability or proportion burned, 4 to 16%, or an average of 7% in those that were significant, 4.7%, 5% across all fires. On the other hand, no plantations burned with greater likelihood than the unmanaged forest. So there's a signal here, there's a difference, but it's not big. Once we had that data set prepared, though, we could look at other things such as forest age and composition. We played around with the broadleaf component, where again, we found some significant effects of broadleaf reducing the amount of fire. So there on the left column, you see reductions from 75 to 67% burn, 83 to 76. Again, not much, but significant. On the other hand, we also found some fires that had greater burning of the aspen leading stands, okay? So I think this is somewhat related to some variations in elevation. That is that the aspen dominates more in the same valley bottoms that are susceptible for other reasons, and south-facing slopes and so on. And also those that have grassy understories. The most deciduous burns happen in spring. There's a couple of articles out recently that talk about the spring blip in global moisture levels and in spring fires that tend to be human caused. But this still remains a big question with a lot of subtleties. So the idea that just because the broadleaves have more foliar moisture content, 150, 170% moisture compared to conifers that are typically under 120, 130%, that doesn't mean they're less flammable all places all the time. So we dove into these patterns of fire resistance. I'm not going to call it resilience, resistance in the plantations a little bit further. And this was led by Alana and Kira Hoffman, and with help from Ingrid Farnell, where forget the categories, they just looked at that satellite-based index, the difference normalized burn ratio from Sentinel-2 imagery before and after the fires, and did a whole data mining exercise there, looking at dozens of potential explanatory variables from the VRI maps, from the results database of silvicultural activities, based on topography, based on fire weather and what rate of spread as near as we could estimate it, and accounting for some spatial autocorrelation. And what fell out from there was a fairly consistent signal of this stand age effect. Okay, so that's in order from top to bottom, the left diagram there, that's plantation age, crown closure, then some spatial autocorrelation issues. Then we get into drought code and some other structural features, maximum temperature. So that's a whole rank list of priorities among 6 of the big wildfires from 2018. Throw them all together for the graph on the right, looking just at stand age. And here we're just talking plantations. We're not talking about old growth. A lot of scatter, but some central tendencies there that match what we've been observing. Okay, so you get a bit of a fire susceptibility for the first 2 years after logging. I would suspect that's related to slash loads. Then you have a reduced or moderate fire susceptibility for maybe another 7 years as it greens up. Then it's high again. I'm not sure why. Maybe as they get crown closure. But then it stays relatively low. You're verging on the unburned category, the green line there from ages about 18 to 40 or more, and then we start running out of good data. So strong signal there. We might group some of those categories into the standard fire behavior triangle of what is affected by fuel compared to weather and topography issues. And it turns out, surprisingly, that fire weather is not the driving factor of burn severity, but really those fuel differences were in 5 out of 6 fires. Now, this should be couched in the terms that these were the big fires that all happened under very high fire weather danger. So we didn't have a lot of variation to test there. But in contrast, a recent study came out by a UVic student with help from some of the CFS folks down in Victoria that looked at all of the fires burned from 1980 to 2020. And so for lightning-caused fires, the set of variables on the right there, that's where the fire weather variables come out on top. For the human-caused fires, the left set of categories, those human-associated factors such as road proximity and community proximity, what they call the EQ mean, were more important, as we'd expect. And that supports some of the assumptions we made in future modeling efforts. They originally started out looking for mountain pine beetle signature. Did not emerge near the top of all fires, but if you looked at fires just that made it to greater than 100 hectares in size, it did become more important in the top 5 or 10 factors. Okay, back to our analysis, Alana's analysis. What effects of different stand management treatments in those plantations? It turns out there are significant effects of a history of site preparation, whether mechanical, mostly disc trenching, or broadcast burning, and a significant effect of brushing and spacing in most cases, but in one of the fires, I think it was the shovel fire, spacing, those stands that had been spaced actually had greater burn severity. So a little bit of a mixed signal there. But it is clear that fuel or vegetation management by altering stand structure and fuel continuity can have an effect some places, sometimes. This does agree with the big picture from the state, a recent meta-analysis showing the benefits of prior wildfire thinning, prescribed burns, and so forth. But here they assessed the lag effect, that effectiveness decreases. Here they made a division between before 10 years and after 10 years, which is not something we addressed, but I would like to. So implications and applications. Yes, we do have fire skips around those juvenile plantations. Stand age is a driving variable, some up and down. We still don't know a lot of the why. Silvicultural treatments can be effective. Notice that this did not test specifically fuel reduction treatments. Okay, most of the spacing, for example, that was done in the results database was purely for silvicultural growth and yield purposes, not really to reduce wildfire susceptibility, which has a different set of rules and guidelines for spacing, pruning, and reducing the continuity of fuels. But all of these activities happen out on the landscape on an annual basis, right? Whether it's planting, harvesting, thinning. So if there are different effects of those treatments, you really need to update your fuel susceptibility, fire vulnerability maps on an annual basis. So now into the why, a little more of an academic question. Why do those juvenile pine plantations have greater fire resistance? So we pursued two hypotheses. This was mostly done in cooperation with fellow researchers at UNBC and with assistance and uptake from Vanessa Ford with the Ministry of Forests. She's a forest climatologist who helped us set up microclimate monitoring stations in open, recent clear-cut stands, typically 4 to 7 years old, in some of these juvenile pine plantations and in nearby old growth. So we had a cluster of 3 sites within 40, 50 kilometers of Prince George, another cluster of 3 sites within 40, 50 kilometers of Smithers. And then we also had students go out as frequently as they could, usually a cycle of every 2 or 3 days, to collect samples of duff, fine woody materials, and foliar conifer foliage to do weighing for moisture content. So that was done in the summers of 2021 and 22. Then the funding ran out for the students, and Vanessa kept going with the microclimate monitoring last year. So a lot of these data have yet to be written up. But in general, the trends seem fairly consistent. Usually the microclimate of these juvenile stands is intermediate, as you might expect, between open and old growth conditions. So this slide shows temperature. The juvenile stands are in red, old growth in green, out in the open in blue. I think this is 2021, so we got our spike there with the heat dome that happened at the end of June. And you can quite reliably predict those temperatures, microclimate conditions near the ground, okay, where that fuel bed is first warming up. Sensors were at about 30 to 35 centimeters above the ground, compared to what's happening at your standard weather station collecting data in the open at 1.5 meters or something like that. And you can see that the conditions are more or less the same at night, under 15 degrees temperatures, and they diverge a little bit more with higher temperatures. But then there's the exception. Sometimes and at some sites, and usually when talking about the extremes, the conditions in the juvenile pine stands do seem to be less conducive to fire. So for example, in our heat dome, and I forget where this was, at the Tamarack site near Tamarack Lake, just west of Prince George, it stayed cooler. We did not quite get the same extreme high temperatures in the juvenile pine stands, obviously, than we did in the open, but also unlike what was achieved in the old growth because of the gappy structure there. Similarly, some of the humidities on the right stayed higher for much of the summer in those juvenile pine stands than you did in either the old growth or the open. Okay, so those are the extremes, the minimum RH, the maximum temperature. So as any Wildfire behavior specialists will tell you often when dealing with wildfire, fire weather prediction, it's the extremes that you're trying to understand rather than what the averages are. And that's especially true when it comes to wind. And here's where we did find a consistent microclimate effect. And that is that winds, both averages and gusts, were always lower in the juvenile pine plantations. And I was worried that we didn't have the technology, but Vanessa stepped up with some high-grade equipment. We're detecting it down to 0.25 meters per second. Okay, my old equipment could only kick in and turn the anemometer at 1 meter per second. There's good evidence that we're not even getting that little bit of a breeze in the juvenile pine stands because it's a very dense, close canopy. It buffers the wind from moving, right? And so that's important if you go to your basic theory of crown fire initiation, paper from almost 50 years ago now. Charlie Van Wagner pointed out that you will only get crown fire spreading if there's an adequate horizontal heat flux with a mass flow of fuel through the flaming front. So the wind is what provides that horizontal heat flux. The wind essentially feeds fuel through the flaming front. If you think of the flaming front as stationary, the wind is like a conveyor belt of fuel into the flames. So you need wind to have a crowning fire. What about the fuel moisture monitoring? Some differences. The duff stays nice and moist longer in the old stands. You can't see his face. That's Clayton Rose, one of our Smithers students who was out there doing the rotation through the sites up the McDonald, down towards Houston, up the Chapman. They were dried in the oven. Again, the BC Wildfire Service gave us use of their ovens and access to tanker base to put these samples through. The fine woody material just dries out more in the open. No difference between juvenile and old growth stands. Conifer foliage, this was a bit of a surprise. Those trees sampled in the open, which were mostly saplings, right? They were a meter or two high, was significantly higher. And there's other evidence again and again that vigorously growing young trees, not the ones that are 20 years old, or maybe we didn't sample the top foliage, just have more juicy material to them, whether it's the woody material or the foliage. But none of this is suggestive of greater fire resistance, more moisture in the juvenile stands than in both old growth and open conditions. Nonetheless, a master student working with Dr. Joseph Shea, Roland Jiao, was interested in looking at the signature since we had the data between those foliar moisture samples and satellite imagery. And there's a relationship there, some possibilities of further monitoring with the NDVI or NDMI code, but again, a lot of scatter. And interesting, some different relationships amongst locations. So, implications, not much happening in terms of air temperature and humidity, but the extremes could be important. And that reduced wind speed, I would say, is now the primary explanatory factor, which would also agree with our on-site and air photo evidence of the behavior of fire when it encounters these plantations. I see Larry nodding, which is greatly assures me. So you see from that, you can see from that photo that usually the fire would venture into the plantations, and you'd see a few spot burns here and there, but it would often peter out in that first 5 to 10 meters or so. Okay, so it's not as if they weren't in there. So again, no fuel moisture differences consistent, but it also gets one thinking that if low wind is important and if fuels dry out more in the open, should we be thinning stands or thinning them too heavily as part of our wildland urban interface fire smart programs. I'm not sure that the lessons that came from the naturally open and gappy forests in the western states applies to our continuous canopy lodgepole pine spruce fir forests up here. Although some of the work from the Rocky Mountains from Colorado would suggest it does still work, but you know, those Rocky Mountain foothill lodgepole pine forests are not really like ours either, so caution. Okay, final stage here, and then hopefully we'll have lots of time for discussion. Trying to put it all together with some fire risk modeling. Now, as many of you probably know, the way this has been done in Canada for the last 20 or 30 years is based on Canadian Forest Service empirical calibrations of fire behavior, primarily in boreal and eastern forests, in which we then group fuel types, the vegetation, into, 16 categories here. The fuel types that are coniferous, deciduous, mixed wood, slash, and open. And they have also supported development of the Prometheus fire behavior model, which is a deterministic wind-driven model. So you see in the center diagram top there, the direction of the wind describes the direction of the fire, and you can implement that for a given land base with the terrain and weather and fuel information to come up with a fairly useful tactical description of fire behavior for an individual fire. Then if you run Prometheus hundreds and thousands of times on a landscape, as they do in Burn P3, another Canadian Forest Service product there, that's the technical report led by Marc-Andre Parisien, you can come up with an overall fire risk or vulnerability on a given landscape. So the problem is this grouping. How do we classify our BC forests into this by now obsolete set of categories from the boreal? And some recent research came out of UBC testing it for the southern interior, and it's right there in the headline: forest types misrepresent forest structure for purposes of fire behavior prediction. So our approach was to just go with the empirical evidence, what burned and didn't burn in the 2018 wildfires. So here another team came forward, building in some of the data sets that Elena and Kira had already assembled. And we now looked at not just the plantations like they did, but the unmanaged forest as well. So Don Morgan headed this up, again using a random forest data mining package, and came up with a number of contrasts between burned and unburned areas using some of those modified thresholds for the DNBR data that I showed you earlier. And there's some surprises in there. Look at that percent broadleaf. Again, unburned areas had only 20% on average broadleaf component, whereas the burned areas at 23. Is that significant? Maybe not. Maybe it's elevation related, so forth. Other parts did agree with some of the things we saw in our ground plots: shorter trees, higher crown closure, a history of site preparation. Some things didn't agree. His analysis showed lower stand density, more likely to remain unburned, likely to burn, whereas our composite burn index CBI plots showed that higher stand densities. Do I have this right? Unburned, less likely to burn. That's right. Okay. We had in our ground plots less likely to burn at high densities. So taking his probabilities of burning from that analysis and applying it to the vegetation resource inventory map for the Lakes TSA, he basically generated a fire susceptibility map. And we can compare that with existing products produced by the province, in which they did try to shoehorn the BC forest types into the CFS fuel types. So that's outlined. The procedure is well documented in a technical report by Dan Parakis of the Pacific Forestry Center. And they did as good a job as they could. So there's some similarities and differences there. You see some clusters of red around places like Burns Lake and Houston, relatively low and in the south-facing slopes. But there's some differences too. Another thing that showed up is you'll notice in the map on the right, produced in 2021, it shows the footprint of the recent wildfires from 2018 as being largely non-susceptible. Okay, those green and yellow areas from the Nadina and the Island Lake and the Verdun Mountain fires, whereas Don's analysis, also based on updated VRI, presumably updated, did not pick out that footprint of previous fires as necessarily being more fireproof now. So that is just a fuel susceptibility map. Then Don and Andrew Fall took that information to calibrate or modify the CELES model, a spatially explicit landscape event simulator. It's been around for 20 years, now widely used for everything from fire risk assessment to timber supply analysis, to develop what he's now calling the TEF model, a time-based empirical model. So again, like Prometheus, it's a wind-driven model with some random offsets. Slope functions as a wind modifier. It's got spotting drawn from a frequency distribution from 100 meters to 2,000 meters. So you need a interpolated wind speed and direction layer from weather stations, collect all the data that's available from those BCWS weather stations, and essentially try to repeat a fire season. So they chose the 2018 fire season. If we were to do it again, we might draw from several big years of fire. Let's do 2018, 2021, 2023. All of them had severe fire conditions. So exercise that model with random point ignitions that are like lightning, supposed to represent lightning, and human ignitions only next to roads where humans tend to congregate. 58 to 42% ratio between the two is the overall average across the province, 58% of fire. We could calibrate that maybe a little more for the north if we want to, and run it 10,000 times. And the map there portrays the number of times a pixel, a 1 hectare area burned. Okay, so those darker violet and blue areas were hit 60 to 90 times. In contrast, the green areas were only hit once. So the first thing that pops out of this map is that strong lake effect. Okay, the big lakes, Babine Lake, Francois Lake, Utsa Lake, do prevent fires from crossing under primarily westerly, southwesterly winds to get to the north or the northeast, the eastern side. But it takes the big lakes. Okay, it didn't matter for just the small ones or the small rivers or roads. So the final experiment then was to test scenarios of fuel modification. Let's say specifically in the WUI around Burns Lake town site, 2 kilometers out, we tested different widths. And here we're talking about not just a cat guard or 10 meters, but 100 meters had no effect. 300 meters, 600, 900 meter buffers, either exposed to 2/3 thinning of what was originally in that forest cover, convert it all to broadleaf, or have no fuel whatsoever. And it had surprisingly little effect, okay, because of that importance of spotting. Okay, the spotting frequency from multiple locations eventually means something's going to cross those barriers. So I think we have to be very careful in promoting fire smart treatments, or even the idea of, I think Kevin was the one who told me, build all your golf courses around town, surround your town with golf courses. That's not going to necessarily work either, because spotting will eventually punch through. So implications, some good agreements with previous studies. some anomalies, especially regarding broadleaf and spacing effectiveness. Hopefully we can contribute these sorts of findings into the next generation fire behavior prediction system that are now being undertaken by the Canadian Forest Service with an emphasis on structure. That fire susceptibility map is probably a useful product in itself for planning tactical and strategic locations for fuel treatments or suppression. But it might be worth comparing why we have agreement or disagreement with the province's strategic threat assessment map. Though the signal from those, that lake effect is certainly noteworthy and something we can test by looking at the extent of fires that historically have occurred or have gotten bigger in those areas. And again, further to our discussion here, fire spread is very sensitive to spotting distances. So we need to improve that calibration as a function of wind speeds and tree heights and the dominant species. And again, no guarantees. So moving on, we now are pursuing another 3 years with the support of the Moore Foundation. And this is a team led by Kevin Crease, with Don Morgan and Andrew Fall, and I think some other people in the room are going to get drawn into this as well. We still have some analysis and write-up to get into the stand microclimate and fuel moisture relationships and their tie-ins with the fire weather maps and remote sensing. I would like to do an expanded retrospective analysis of regional wildfires over the last 10 years, starting with those that are greater than 100 hectares, not just those greater than 10,000, to further refine the DNVR thresholds, take account of time lags of previous fires and mountain pine beetle. We need to have a better handle on when did each pixel or hectare of land burn, was it day or night, what time, what date exactly. And also, I just met with Brad Martin yesterday afternoon to look at the feasibility of first filtering out where the suppression efforts were, because we didn't do that before. We didn't discount where fuel guards had been put in place or where air tankers had been operating or where backfires had been lit. So I think we can do a better job yet. And we need to tap into a lot of the knowledge that people like him, like Larry, have in their heads. Dana Hicks and Prince George, local knowledge, traditional ecological knowledge. What stops fires under different conditions? We could maybe make a set of if-then rules to add to our modeling efforts. And we should also consult with communities and forest managers to find out, well, what management scenarios are realistic to test. This now is going to focus on the Bulkley-Maurice watershed as a whole. And hopefully we'll have some, improved estimates and empirical data to support the spotting and rate of spread as well. So we do still have some time for questions. So thank you for your attention, and let's talk about it. It's imperfect, but I think we've got some interesting results here.
Oh, okay. I think the video has come to an end. So as the professor has suggested that although the effects of droughts and day-to-day fire weather, which particularly wind he mentioned, are strong, like some differences in the land age, the structure and composition evidently can reduce the likelihood of the crown fire and may have been marginally useful in proactive landscape planning to enhance the fire resilience. I think so that will be all the materials that I have prepared for today's lecture. And do you have any questions?
It's really a very good lecture. I don't really have good questions, but what Professor said, it was almost new to me. So I just learned some good things, and I really appreciate of our invited professor. to deliver a lecture to us. And hope to see the professor again. I hope our class teacher will bring him again, because there are lot to know actually about the land fire and other things in Canada and global perspectives. He discussed about the Canada, but some other forest fire in the Asian country, we also need to know about it. So thank you so much, Professor, for your kind lecture. Thanks,
Thank
our
you so
class
much.
teacher too.
Thank you so much
Bye.
for attending today's course. And actually, I'm not a professor, I'm a PhD student. And yeah, I'm currently doing my PhD programs. And I'm super happy that you find something interesting from this lecture. And yeah, if you have any questions about the wildfires, especially in Canada, which is also my current research area, please feel free to contact me. And yeah, thank you so much.
So I just have a quick question.
Mhm.
So what do you think, like a severe forest fire, how it can damage a watershed, a natural process?
So I think the wildfire is actually the natural disturbance instead of the human caused disturbance like the logging, which is also caused the harvesting. So the wildfires can be ignited in some can be happen. I mean, it may happen in some specific conditions, like if the forest is the fuel is enough, like the weather is favorable for the fire weather, and of course, the topography, which is also an influencing factor that can affect the fire behavior. So, in the previous, like the 2 or 3 centuries, the Canada has experienced like some wildfires without the human disturbance. In the previous 2 or 3 centuries, the human disturbance you can consider is as minimal, but the wildfires still happen, and we can consider at a natural regeneration process. Like after the wildfire, the vegetation composition can be changed, and like the shrub will appear first, and the vegetation will appear afterwards. And I think the wildfires in recent years that have attracted our attentions, that is because of the global warming, the wildfires have threatened the human local areas. And therefore, the stream flow will be affected. Like, the forest is a natural resource for the water that we everybody use. And if the wildfire can change the water and like the stream flow pattern, like the magnitude, the timing, and it will afterwards affect the local areas. So, for example, like the wildfires can affect the soil infiltration. That means that in some specific areas, there will be more floods than what is used to be. So it will definitely affect the local community's normal life. So I think at a good point, many people in Canada here are trying to use some management strategies like using the prescribed fire to reduce the canopy, which is also like the fuel, the fuel that can be used for using the vegetation can be used as a fuel for the fire. And on top of that, the topography, as I talked before in the slide in the lecture, like the topography can be using as a natural wildfire break in the real life scenarios. So I think it may have some implications for the local, like the watershed management for the wildfire resilience. Yeah, I think your question is quite in general, and I wonder if my answer is is right for your answer. So, yeah.
Thank you so much for your clear clarification. I appreciate. That's all
Yeah,
about from my side.
And I also saw a question from Bala, and having known that there are depths about the watershed stream flow after wildfire, there are key factors that determines how a wildfire affects the watershed stream flow and what general trends can we expect in stream flow after a wildfire event. Yeah, I think I talked it in my slides. You know, so in general, the annual mean flow will typically increase after the wildfire in most watersheds, but there are some cases like some watersheds that having a really large area but experienced the wildfire that burned a small fraction of the area. On top of that, the post-fire weather, like the climate variability, may mask the effect of the wildfire's increasing effect on the stream flow, and therefore they will show not and decreased stream flows. While for the peak flows, the peak flows often like in the magnitude perspective, it often increased because of the soil infiltration rates decreased, as I taught before, and it will timing the timing of the peak flow will change, like the timing, like the wildfire may appear more earlier than what it used to be. And while for the low flow, and I also talked before, the low flow is not is kind of site specific. In some watershed, the low flow may increase because we have more water that can be available because of the canopy have been reduced and the precipitation can reach to the ground. There are more water for the infiltration. But however, as we talked before, the infiltration will reduce. And although we have more water, the groundwater recharge may be affected, and therefore the low flow will be affected. So the low flow is kind of site specific, and we need to do the analysis based on the watershed characteristics. Yeah. Okay. So I think do you have any more questions? Please, you can call me or you can contact me through the email. And so that will be all for our today's lecture. And thank you so much for attending today's course. And thank you so much for the invitation from the Professor Wang. And I'm really appreciate for having such a grateful chance to talk with you. So thank you. Have a great day, and bye.
Thank you very much. Bye-bye.
Thank you so much. Is this class over today?
Yeah, the class over, and you are good to go.
Oh, thank you. Thank you so much. Thank you.
Have a great day. Bye.
Have a good day. Probably tonight in Canada. Take rest. Good rest.
Yeah. Bye.
Bye-bye.